So now let's talk about the strength of an acid or a base. So if I have a couple of structures and maybe they're not on the chart, or I just don't remember them off the chart or something, and I want to say who's going to be stronger or weaker. How do I know that? Or how did that chart get created? How do they know who is strong and weak on that chart? So let's look at this. So what makes a strong acid strong? Okay. So if I'm making a strong acid, we said that a strong acid completely dissociates. It's going to break apart. So if I need it to break apart, I need the bond between, remember an acid is an H plus either a non-metal or polyatomic. I need this bond to be easily broken. So if I want it to break apart easy, I need a weak bond there. If this is a weak bond, it's going to separate easy, so then my H plus can be easily removed. All right, so let's look at our binary acids. So remember we call binary acids the H with just the non-metal. So let's look at these guys. So look at our bond energies. This is a low bond energy, and then it goes higher to the bond energy. So if it's a low bond energy, it means that this bond right here is pretty weak. So if it's pretty weak, I can break it really easily, and if it's easy to break, I can make it a strong acid. So as my bond strength gets higher, it's harder for me to break it, so the strength of my acid gets weaker. So as my bond energy increases, my acid strength decreases. Okay? Now, we're going to talk about Kas. This is the same K we did with Kcs and Kps, where it was our equilibrium. But we're talking about it specifically. So when we did Kcs last chapter, that was for anything. This chapter, it's just like those. Same things, everything we did last chapter with concentrations with our Kc, we could do here. It's just Ka because it's specifically for an acid. Okay? So, if my number is high, it means that it's going to dissociate really easy. It's going to go towards products really easy. Remember, if the K is bigger than 1, it goes to products. Products is separating. If it's less than 1, it doesn't want to go to products. It's not going to separate as easy. Because remember, here's my reaction. They're together, and then they're apart. They've separated. So if it's a strong acid, it's going to go completely over here to products. All right, so here, the higher the bond energy, the weaker the acid. Now let's talk about if it's a oxyacid. So remember, oxyacid, you had your H, and then you had a polyatomic ion. So these kind of look like you've got your H, your O, and then your non-metal. So we see it like this, HOZ. So the same thing applies. If I want this to be a strong acid, I need this H to pop off. So if I need this H to pop off, this bond has to be weak. If this is a weak bond, then the H is just going to pop off to be my H+. So I need a weaker HO bond. The weaker the HO bond, the stronger the acid. This is the same like we just did on the previous slide. But how do we make it weak? How do I make this HO bond weak? This HO bond is going to be affected by the OZ bond. Okay? So, if Z is really electronegative, remember electronegativity increases up and over. So fluorine is the most electronegative. So if this is really electronegative, it's going to pull the electrons towards it. Okay? So if it pulls the electrons towards it, it makes this bond weaker. So the larger the electronegativity of Z, of whatever this element is, the weaker the bond. So here, chlorine has a high electronegativity. So it's going to pull everything over. It's going to make this bond really weak. So it's going to be a stronger acid. Now you might say, well, this is still a negative, but in comparison, It's stronger in comparison. Because remember, this whole point is to be able to compare. So if I gave you these three guys and I said which one would be the strongest acid out of them, then you have to be able to compare them. Okay? He has a lower electronegativity, and we don't even have to know these numbers. We could just look on the periodic table. So on the periodic table, this goes F, Cl, Br, I. So as I'm going down, my electronegativity decreases. So I don't even have to have the numbers. I can just predict it. I can say, okay, he's got the lowest electronegativity, which means this HO bond's going to be stronger, which means he should be the weakest acid. Okay? So, our rule, electronegativity increases. Then we have a weaker HO bond. So, electronegativity increases. We could say HO bond decreases, so then my acid is stronger. So the stronger the electronegativity, the stronger the acid, right here. Larger the electronegativity, the weaker the bond, the stronger the acid. All right, now this is if I have 1O, and the only thing that's differing is here. Here, this is similar, but I've got 1O, and then I've got the Cl, but the difference is the amount of O's on the Cl. So it's still HOZ, but my Z is a group of atoms. So I have a bunch of different atoms. All right, process is the same. If I want a strong acid, this bond has to be weak. So I need a weaker OH bond. The weaker the OH bond, the stronger the acid. The way that I make this bond weak is that I need the electrons to be pulled over here. I need to talk about the electronegativity. But all of these guys are chlorine, so they all have the same electronegativity. The difference, though, are these O's. One has 3, 2, and 1. These O's are what we call electron withdrawing groups, which means they're going to pull over the electrons, because oxygen is electronegative itself. So, what this means is the more I have a chlorine and 3 O's. There's a lot of things that are electronegative pulling it over. The more electron withdrawing groups, the weaker the bond, the stronger the acid. So what we could say is the more oxygens, because the more O's, the more electron withdrawing groups, the more electron withdrawing, the stronger the acid. Okay? So more oxygens, more electron withdrawing, stronger the acid. All right, now let's talk about the pairs. So we can look at one thing and know if it's going to be strong or weak, but we need to talk about these conjugate acid-base pairs and their strength. All right, so say I have a strong acid. They're really good H+ donors. They're like, yep, I'm going to donate, I'm cool with that. Their strong acids are better H+ donors than weak. That's just their definition. And their conjugate is a conjugate base, so strong acids have a conjugate base. If the acid is strong, because they're going to be so good at donating, that their partner is going to be a weaker base. Because remember, bases are going to be acceptors, and these are donors. These want to donate a lot. So if they really want to donate, they're making this guy weaker. Kind of the opposite. All right, strong bases are better acceptors than weak bases. Okay? So if I have something that's weak, base or an acid, doesn't matter. In this case, I'll say if I have a weak acid, my conjugate is a base, because it's always the opposite. If one's gaining, one's got to lose, and etc. If it's a weak acid, then it's going to be a stronger conjugate base. Okay? So it's always the opposite. If this is an acid, this is a base. If this is weak, this is strong. Always the opposite. All right, so let's look at this guy and let's label him. So I have my HCl. Who's his partner? It's got to be whatever has a Cl. He has a Cl. So then these guys have to go together. What's happening from here to here? Is he gaining or losing the H? He loses the H+, which makes him an acid. If he loses the H+, and he's the acid, that means his partner is the base. All right, let's do the other guy. What happens between here and here? He is going to gain. So he gains an H+, so that makes him a base. If he's the base, his partner is the acid. Now, another thing you should notice that you won't ever have two of the same thing on the same side. So he's an acid, he's a base. He's an acid, he's a base. But just when we figure out this one, don't automatically say he's a base. Look at each one and their partners on the other side individually, and then this is a good check to make sure you didn't screw it up. Now we want to know the strength. So there's two ways you can know the strength. One, you can know this guy off the chart, or the fact that this is a single-headed arrow. So if it only goes in one direction, we know that it's got to be a strong. So if he's a strong, if he's a strong acid, then what does that make him? This makes him a weak base. Okay? And you only have to do it, we don't really talk about water. We just talk about the guy that's doing something. We don't really talk about the strengths of the other ones. All right, let's do the next one. Here's HF. Who's his partner? The one with the F. All right, let's look what's going on. From here to here, is he gaining or losing? Okay, he's going to lose an H+. That makes him an acid. That makes him a base. Then let's look at the water. What's the water doing from here to here? He's going to gain an H+, which makes him a base. Makes him the acid. And then we do a check. See, I didn't automatically say this was a base because he was an acid. I thought about him by himself, and now I check. Oh, yep, one of each, so I know I didn't screw it up. Now let's talk about the strength. You could find HF in your table. He is in there. And you could look at this. It's a double-headed arrow. So if it's a double-headed arrow, that means that it's going to be weak. So if he's weak, he's strong. Okay? It's always the opposite. All right, let's look at a summary table. So this is a good summary table. So I have my strong acids up here, my weak acids. I can do the conjugate. So he's an acid, he loses an H+ and gives me my base. If he's a base, he gains the H+, gives me my acid. So I could write the conjugates. If he's strong, he's really weak. If he's strong, he's really weak. Okay? So I can write it and make it the opposites. All right, let's look at this problem. So it says, is the following aqueous reaction product or reactant favored? So it's going to be based on who's the strongest. So the strong guy is going to be the determining factor. So let's look. So we've got NH4+. Here he is on our chart. So he's here. And let's see, it's him. And who's his partner? Him. And then these guys are partners. NH4 is here. So he's kind of a weaker acid. Okay. And then, so he would be a weaker acid. F, kind of a weaker base. NH3, he's stronger base. He's a stronger base. In comparison to my F- is stronger. So NH3, because look, it's going down in strength. Like this is strong, like our last chart. So just because it's going down doesn't mean it's going down in strength, because it's opposites. This one goes up and this one goes down, so they're diagonal. So NH3 is going to be stronger than my F-, so stronger base. HF is a stronger acid than my NH4+. All right, so now I kind of have everybody labeled. So stronger means he's the one that wants to ionize. So stronger means greater tendency to ionize. Okay? So if these guys are both stronger, it says they want to do everything. They want to separate, they want to ionize, so they're going to push everything this direction. So they're going to push this direction, so which way is it going to be? It's going to be reactant favored. Now, if you had a strong on each side, then you have to pick who's the strongest one out of that pair. So whoever's the strong one, if they're both on the same side, then it's really easy. But if one's on one side, one's on the other side, you have to say, well, who's the strongest one out of all these guys, and he's the one that makes the decisions. Okay? So the strong one is going to push the direction. All right, so we're going to stop there. So we talked about strength. The next lecture, we're going to talk about that K. Remember we saw the Ka right here. We talked about what kind of it meant. We're going to talk about that. And then we're going to talk about what water does. And what is water's role in all of this. Okay? So that's your next lecture.